Handheld computers are becoming commonplace. Their small size makes them portable and convenient, so you can carry one with you all the time. But if you've ever tried to draw a map on one of these things, you know it's a real hassle. All of the advantages of a small size come at a high price, a tiny, impoverished display. It would seem that all handheld computers must necessarily have displays much, much smaller than the surfaces people typically use for viewing and interacting with information. This limitation is an issue for cell phones as well as personal digital assistants. It would be nice if we could have the convenience of a small device without losing the flexibility of a large working area. But how can you have a display that's bigger than the device? Here's one approach. Suppose you imagine that the information exists in a big working area in the space in front of you. The screen on your handheld device gives you a peephole on just a part of this space, and you can move it around to see different parts. In one of the implementations I built, the position of the handheld device is measured using a mechanical mouse and 2 pieces of fishing line. Each line runs from the handheld device to a reference point, and then around the shaft of one of the optical encoders in the mouse. Tension is maintained with a small weight on the end of each line. The mouse reports its X and Y coordinates to a computer, which tracks the distance from each reference point to the handheld device. The computer triangulates the position of the device and transmits this information along a cable to the serial port on the device. In practice, this turns out to work pretty well for navigating information. Here, I'm browsing a list that's much longer than one screen. Notice how the list appears to float fixed in space as I move the handheld computer in the air. Because the list occupies a fixed position with respect to my body, spatial memory enables me to navigate between items very quickly, even when they are a couple of screens apart. We can also view two-dimensional information this way. Here I'm looking at a fictional subway map that's bigger than the screen. Since I don't have to operate scroll bars or a pen, I can comfortably browse the map using only one hand. Here, I'm using a simple drawing program. I can reposition my view using my left hand while writing with my right hand, so it's easy to write lots of text. This could be great for note-taking. Now I'm using the same drawing program with different hardware. The position of the handheld is tracked on a tabletop by an optical mouse. By using both hands together, I can easily draw figures much bigger than the screen. For example, it's easy to draw a line in a single stroke that accurately joins these distant points. This would have been very difficult in a typical palm-top drawing program. Or consider trying to draw a circle much bigger than the screen. Using the peephole technique, it's straightforward to draw in a single stroke, with consistent curvature and accurate closure. It's nearly impossible to do this well using traditional panning techniques. 24 people participated in a user study. Details are in the paper, but the summary is that for some tasks, especially for drawing, people found the interaction technique natural and effective, and most of them even thought it was fun. After the user study, a more advanced prototype was developed, using a 3-dimensional position tracker and a PDA with a color screen. There are many possible ways to use the additional depth information. One obvious possibility is to use depth to control zooming. Here, I'm looking at that subway map again. Lifting the screen lets me zoom out. Now, I can smoothly zoom and pan at the same time with a single gesture. Here is the peephole technique applied to a more traditional PDA application, the datebook. An entire month of events can be viewed in the workspace. In this example, lifting the screen switches to an overview of the whole year. Here's a simple drawing application. Objects can be dragged all over the workspace. In this example, lifting the screen flips to the clipboard view. Objects can be dragged and lifted up to the clipboard. We can also push them back down to paste them onto the canvas. In a mobile setting, the screen tracks its position in the user's physical reference frame. This enables text, graphics, and user interface widgets to be arranged in the space around the user's body. This personal information space might contain multiple documents and multiple applications. To illustrate this concept, I'm now wearing the position tracking equipment. It's mostly portable, except that it still has to be plugged in for power. In the future, we might imagine using a tracking system that's smaller and powered by a battery. Let's see how we can do this time. In this example, I have 2 applications in my personal information space. There is a calendar application on my left and a sketchpad on my right. I can draw a large map on the sketchpad using two-handed peephole interaction techniques. When I'm done drawing the map, I can pick it up, drag it over to the calendar, and link it to the scheduled event. Later, when I'm browsing the calendar, an icon next to the event indicates that there is an attached drawing. If I select the event, the calendar directs me over to the sketchpad to view the associated drawing. The concept of a personal information space opens many interesting possibilities for interaction on handheld devices.